So by weighing the crown first in air and then in water, suppose the scale reach 7.84 Newton in air and 6.86 Newton in water, what should Archimedes have told the king? Suppose the scale reached 7.84 Newton in air and 6.86 Newton in water. What should Archimedes have told the king? Take the density of gold. Take the density of gold to be 19.86 gram per cm cube. 19.86 gram per cm cube. Of course, once all other variables are given in SI units, you can change this density in kilogram per meter cube. And don't forget, the crown was immersed in water, so the density of water will be used. So if you are Archimedes, what will you tell the king? Okay, I'm giving you 10 minutes. I think 10 minutes is so much. Okay, 10 minutes to think through the question. Let's see how you can go about the question. You are to take the density of pure gold to be 19.86 gram per cm cube, and the density of water is 1 gram per cm cube. Start work. So what will you tell the king if you are Archimedes? Don't tell me you are not Archimedes. All right, start work. If you have any question, you can ask before. Is there any question? Okay, start work. You are free to start. Whoever is ready to share what he or she managed to do. So, Saki, Genius Saki, if you are Archimedes, what will you tell the king?
Sir, please, the mass of the gold used.
The mass of the gold used is.
Sir, please, I wasn't done yet, but I
Okay.
got it in.
Then go ahead and then complete it. Anita, let me hear from you. Anita, what will you have told the king?
Please, I'm not done.
Okay. So whoever is free can share whatever you had with me. The door is open. Emelda, when you are Frank, Gideon. Okay, Trum, I'm listening. Oh, Trum, go ahead. I'm
Yes, sir.
listening. I'm listening.
Say, please. The Archimedes should have told the king the crown appears to be made of pure gold based on its density.
The crown is made of pure gold based on its
Yes,
density.
yes.
What did you have as the density of the crown?
Please, 19.3 gram per cm cube.
Okay, that's what Benjamin had. More views. More views before I come in. Yes, Gideon.
Sir, please, the crown was not made of pure gold.
What's your reason?
Sir, please, because when you look at the density of the gold and the density of the crown itself, when they are not the same. So there was some 0.07 part of the crown which was not made of gold. So which
So,
makes the crown not pure gold.
so Gideon, what did you achieve as the density of the crown?
19.79.
No, that you mean the 19.79. Okay,
Yes, sir.
okay. All right. Benjamin, your hand is up
Yes,
again.
sir. Say, please, since the calculated density is 19.3 gram per cm cube, it's approximately close to its actual density. So it means it's a pure gold. It's made of pure gold.
Okay. Her last contribution from a lady. The gentlemen have actually expressed their views. So, Asida, you are here. Antoinette, Anita, Nana Kumi, Elitea, Ida, you are here. Daisy, you are also here. So let me hear from you. When you are Emelda, Asana, you are also here. All right. So let me share the screen and then take over. Yes, I'm coming. Okay, so what and what do we have? We have the, please, when you join, quickly mute yourself for me. So the question says that Archimedes supposedly was asked to determine whether a crown made for the king consisted of pure gold. And legend has it that he solved this problem by weighing the crown first in air and then in water. And then suppose the scale reads, or the scale read 7.84 Newton in air. So it means that we have weight of the crown. It was the crown which was weighed in water and in air. Weight of crown in air, we have 7.84 Newton. Then its weight in fluid or in water, weight of crown in water, this is equal to 6.0 86 Newton. Okay, what should Archimedes have told the king? Considering that density of gold is equal to 19.86 gram per cm cube, and density of water is also 1.0 gram per cm cube. Okay, so to solve this, obviously we must determine the density of the crown and then compare it with the density of pure gold. If the crown is made of pure gold, our expectation is that the crown must have this almost the same density as the density of pure gold. If the densities are different, then it will be evident that perhaps he took part of the gold and alloyed, okay, what was left, and then made the crown with. That is the conclusion. So we are to determine the density of the crown and compare it with the density of pure gold. So how do we do this? We know density of crown must be equal to mass of crown divided by the volume of crown. We can determine mass of crown from its weight in air. So the mass of the crown, mass in air, of crown in air will be equal to its weight divided by acceleration due to gravity. So the weight in air is 7.84. Acceleration due to gravity 10, meaning the mass of the crown is 0.784 kilogram. Class, are you following? Are you okay up to this stage?
Yes, please.
Okay. So the next issue to look out for is to determine the volume of the crown. And we can determine that from weight in air minus weight in water is equal to upthrust, which is rho Vg. The weight in air is 7.84. The weight of the crown in water is 6.86. Density of water, 1. So 1 times volume we don't know. Gravity. Okay, so in this case, because we are dealing with weight, let's change all values to SI units. So the density of water, 1,000. Volume of water displaced is what we are looking for, times acceleration due to gravity, 10. Therefore, what's the difference between the real weight and apparent weight? Emil, I'm listening. 0.98 divided by 10,000, 10 to the power 4. This is equal to 9.8 times 10 to the power negative 5 meter cube. Are we okay? This is the volume of water displaced. And since the crown is fully immersed in the water, the volume of water displaced is equal to the volume of the crown. The volume of crown is therefore 9.8 times 10 to the power minus 5 cubic meter. Once we have the volume, we are good to go in determining the density of the crown. Density of the crown, therefore, is equal to its mass 0.784 kilogram divided by the volume, which is 9.8 times 10 to the power -5. This is also equal to 0.784 divided by 9.8 times 10 to the power 5. Please calculate that for me. Divide 0.784 by 9.8 and multiply that by 10 to the power 5. Imelda, I'm listening. Anita, I'm listening. Frank, I'm listening. Yes, juniors.
Sir, please, you get 8,000.
So this is 8,000 kilogram per meter cube. Let's also express this density in gram per cm cube. Express 8,000 kilogram per meter cube in gram per cm cube. Anita. Hey, you girls are quiet. What is your secret? Okay, anybody can call it. Juniors. Convert density of 8,000 kilogram per meter cube to gram per cm cube. Hey, Assembly, you are not talking. Ferdinand, Rempoma, Gerard. Nana Quintua.
Sir, please, 8 grams per centimeter cube.
Thank you. 8 grams per cm cube. Just divide by 1,000. If you are converting from gram per cm cube to kilogram, multiply by 1,000. So this is it. Now look at something. Compare this to the density of pure gold, which is 19.86. Saki, your hand is up.
Sir, please, why did we multiply it by 10 raised to the power 5?
Oh, you see, when I divided, you see, we have 0.98 divided by 10 to the power 4. Let's change 0.98 to standard form. This is 9.8 times 10 to the power -1. When 10 to the power 4 comes up to multiply this, then it must be 10 to the power. Okay, let me even take my time. So we have this column. Please let me pick this call and get back to you. Hello? 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 Ah, I need you. All right, let's continue. So we have 9.8 times 10 to the power -1 divided by 10 to the power 4. Okay, this is equal to 9.8 times 10 to the power -1 minus 4, isn't it? So we'll end up having 9.8 times 10 to the power -5. This is how come I multiplied by that. Okay, so when this is the volume of the crown. So if you divide through by the mass, and then you are bringing it up, it's going to be 10 to the power 0, 10 to the power 0 minus 5, isn't it? And so 10 to the power 0 minus 5, this will be 10 to the power 5, positive 5. So that's how come I multiply that by 5. Please, are you okay? Hello?
Yes.
Yes, please.
Okay. Hello? Mm-hmm. Mami si, radio, mami, why? Mami, we are radio, mami, na mami. All right, so that's it. Now, when you compare, plus, when you compare the density of the crown to the density of the gold, okay, there is huge difference. There is huge difference. So how would you conclude? If the density of the crown is 8 gram per cm cube and the density of gold is 19.86, how would you conclude? Yes, I want one of you to conclude it for me. What will you tell the king?
So please, the the crown is not made up of pure gold.
That's one. Zaki. So,
Due to the vast difference in densities, the
mhm,
crown was not made out of pure gold.
exactly. Yes, I'll send you more questions. Okay. It's a very nice, interesting question. So I'll send you more questions after today's class. And Anatrum.
So please, since the calculated density of the crown is significantly lower than that of the gold, it suggests that the crown is not made of pure gold.
Exactly. So look at 19.86 and 8, not even half. So it is obvious that the guy took part of the gold and then alloyed, okay, what was taken to make the crown with. And so he stole part of the king's gold. That's it. That's the solution to the question. Okay. All right. If you have any question, ask. If you don't have any question, let's continue with flotation. 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 Please, when you join, kindly mute yourself for me. Flotation.
So please, can you please, I'll just check something.
Hey, Gideon. Okay, quickly write it in it. Anita, are you there? Imelda, are you there?
Yes, please.
Anna, are you there? Please, the ladies, try and then be asking questions, okay?
So please, I'm done. Thank you.
Okay. Flotation. Flotation.
Flow.
Let's first look at the principle of flotation. The principle of flotation. Flotation, this is American spelling of flotation. The British spelling is FLOATA. I think we must follow the British because that's the kind of English we study. Now, what are for a body to float, what are the conditions? For a body to float, what are the conditions? Conditions necessary for a body to float. Yes. You learned one of the conditions in GHS. Saki.
So please, it has to have like a hollow shape.
A hollow shape. Okay, yeah, Saki. More views. Which other hand is raised? I'm coming. Hey, Extra. Today you've joined us from Cote d'Ivoire. Okay, Frank.
The volume of the body must be equal to the volume of the liquid displaced by the body.
Well, whenever a body is in fluid, yes, the volume of water displaced or the fluid displaced is actually equal to the volume of the object. That is always a must, but not a critical factor for flotation. Okay, more views. More views. Oh, you learned one of the rules for flotation in DHS. Gideon.
So please, its density must be lesser
Exactly.
than the density of water.
Exactly. So for a body to float, the density of the object, please mute yourselves. Density of objects must be less than the density of the density of the fluid. Trim, your hand is up.
Yes, sir. Say, please, the body must displace a volume of fluid that weighs at least as much as the body itself.
Come again.
I said, please, the body must displace a volume of fluid that weighs at least as much as the body itself.
Okay, yes, that's the second one. Thank you. Another hand is up. This hand is from Gerard. Gerard.
So please, if an object average density is greater than the density of the fluid, it will float.
If it's greater, it will sink. It must be less rather.
Yes, sir.
So cooking oil floats on water, meaning the density of cooking oil is less than the density of water. Kerosene, petrol floats on water. Density of kerosene, petrol must be less than the density of water. So for a body to float, the density of the object must be less than the density of the fluid.
Yes, sir.
Two, the second point is what Trum said. For a body to float, the weight of the body, or let's even talk about weight. The weight of the body must be equal. Weight of body must be equal to the weight of fluid displaced by the body. Weight of fluid displaced by the body. So weight of fluid displaced must be equal to weight of body must be equal to the weight of fluid displaced.
Yes.
Okay. Weight of fluid displaced is the same as upthrust. So we can also state this in terms of upthrust, that for a body to float, the weight of the body must be equal to the upthrust exerted on the body. Nana, Chum.
Yes, sir. Sir, please, if the surface tension is also strong enough, it can support the weight of the object and cause it to float. Oh,
And that is also due to the same upthrust.
okay.
Okay.
Thank
So
you, sir.
for a body to float, weight of the body must be equal to the weight of fluid displaced by the same body. And this weight of fluid displaced is what we are also describing as upthrust. So the principle of flotation states that a floating body displaces its own weight of fluid. A floating body displaces its own weight of fluid, meaning the weight of fluid displaced must be equal to the body's own weight. So a floating body displaces its own weight of fluid. Please, I hope it is clear. Ida, are you there?
Yes, please.
A floating body displaces its own weight of fluid. Frank,
I don't understand the point you just made.
come again, Frank.
I don't understand the point you just made.
What I'm saying is that the principle of flotation states that, you see, we just said that for a body to float, the weight of the body must be equal to the weight of fluid displaced by the same body. So weight of fluid must be equal to weight of fluid displaced. Weight of body equals weight of fluid displaced. And so we can say that because the weight of fluid displaced is equal to the weight of the body, we can state the principle as a floating body displaces its own weight of fluid, meaning the weight of fluid displaced is equal to the weight of the same body which is floating. That's the principle of flotation. Meaning, if a body floats and the weight of fluid displaced by the body is not equal to its own weight, it cannot float. Genius, your hand is up.
Yeah, please, can you say that one of the conditions necessary to float is it has to have a streamlined body?
Yes, it is not a condition. All the streamlined body thing are all embedded in this one, the second principle. Okay. Its streamlined body would enable it to displace more fluid. Okay, so it's embedded in this. Now, because weight, Frank, last question, so we move on.
Can you also say that the objects displaced must not be permeable in order to
Must not be. Oh,
permeable?
and yes, if the object is permeable, okay, then its density will be greater than the density of the fluid. Okay, so they are all embedded in the first and second condition. If the object is permeable, if you have a canoe and the canoe is permeable, water will fill it. Once water fills it, its density will be greater than the density of the water and it cannot float. It will sink. Ella.
Yes.
Mm-hmm.
Yes. And please,
Um, an object which has an object which is hollow can also float. So isn't that also a condition?
That is also within the second principle. And I'll go into it well. So you hold on. As we move on, I'll be explaining, okay? Gideon, hold on. Let's continue and as we move on, if you have any question, you can. Okay, so somebody is asking, Aptra's force must equal, okay. So why is it that if a ship is sailing on water, it doesn't sink, but if you put pin or even small stone, gravel in the sea, it will sink? So I'll answer it. So weight of the body must be equal to weight of fluid displaced or the Aptra's. Now, weight is equal to mass times acceleration due to gravity. What it means is that mass of the body can be equal to, weight of the body can also be equal to mass of the body times gravity. And this will also be equal to mass of the fluid displaced times gravity. J and J would cancel out. And we can also have mass of the body being equal to the mass of fluid displays as. So the second condition can be said in terms of either weight or mass. So we can also say that for a body to float, the mass of the body must be equal to the mass of fluid displaced by the same body. Okay, so class, all that I'm saying is that the second condition can be stated in terms of weight or in terms of mass. Are we okay? Class, are we okay?
Yes, sir.
Cool. Now, the density for a body to float, the weight of the body must be equal to the upthrust. And upthrust is equal to rho Vg. This means that for a body to float, the extent of the body's flotation depends on the density of the fluid. Okay, the extent of the body's flotation also depends on the volume of fluid displaced. So when the fluid is denser, the body can float more. Are you listening? If the fluid is denser, it will make this upthrust. When rho is greater, since the upthrust is equal to the product of these three. When rho is greater, upthrust will be greater. If upthrust is greater, the body will sink, will float more and sink less. If volume of fluid, V, displaced is greater, okay, the upthrust will be greater as well. If V is greater, upthrust, which is rho Vg, would also be greater. So these are factors which determines the extent to which a body would have floats. If the volume of fluid displaced is greater, the object will float more. If density of the fluid is greater, Okay, so it means that when you put a body in oil, cooking oil and water, the object must float more in water than in cooking oil. This is because water is denser than cooking oil. Class, are you following?
Yes, sir.
Okay, so the extent of flotation is determined by rho and V. For V, if a body is floating in water, we have no control over the density of water unless we decide that, oh, we want to make this water denser. So let's pour lots of salt into it so that it will change the density. But we can't do that. So if a body is floating, we can only affect the volume of water displaced by the body. And how can we do it? We know that when a body is submerged in a liquid, the volume of water displaced is equal to the volume of that part of the object which is submerged. Okay, so this is the reason why for any floating body, it is designed to ensure that the body has a larger volume. So because before wood can float, it has to be the tree after it's been cut. We must carve parts of the wood out. As we are carving parts of the wood out, all that we are doing is that we want to increase the volume within. If there is larger volume within, then the wood which will be on the surface of the water will displace large volume of water. If large volume of water is displaced, it will affect the upthrust. Now, Augustine, your question. Large boat would float and even a small stone will sink because large boat is designed to have a hollow space or cavity within. The hollow space within ensures enables it to displace huge volume of water, which will increase the upthrust it would experience. Now, for the small stone, there is no hole, and so the volume of water displaced is so small, and this does not increase the upthrust, which would balance its weight for it to float. This is why the stone will sink, but the boat would also float. Augustine, have I answered your question? So ships are actually built to have space. A ship is not a complete solid block. Okay. Yes, it can take cargo and all that, but it is designed to have large volume so that when it is on the surface of the ocean, it can displace large volume of water, which would also affect the upthrust. When the upthrust is large, it would balance the weight, the entire weight of the ship, and it can float this time around. Please, if you have any question, ask. Now, the streamlined body you spoke about. The streamlined body enables it to push away large. Yes, this is what you are saying as a streamlined body. The edges is shaped like this. A canoe, boat, submarine, or whatever. This edge enables it to just push away large volume of water easily. So they are all embedded in this. If the surface is just like this, it cannot display, it would even experience a lot of resistance, drag between the water and then the object. So that is why, in order to displace large volume of water, and then just move through the water easily. The reason why it is designed to have a streamlined shaped body. Please, are you okay? Hello, are you okay?
Yes, please.
Now, when ships offload goods at the harbor, ships are not allowed, they can't even go. But they are not allowed to sail when they are empty. A ship comes from maybe overseas, offload goods at our ports. When it is going, it is never allowed that the ship would go empty. If there is nothing to load the ship with, it must be filled with sand. Sand in a bag. If there is nothing to even load the ship with, when it is going back, it must be filled with sand. Sand. Can you think of the reason why a ship is not allowed to sail empty? Can we discuss? Yes, Gideon. Start.
So please, I think because if the ship is allowed to go empty, it will displace less volume of water since it has been made lighter. But if it is filled with sand or with goods to go with, it will displace a larger volume of water, which will help it float more.
Okay, thank you. That is Gideon's view. Godfrey. Godfrey, please go ahead.
Please, it will not be stable.
Explain.
Um,
Can you explain?
Not really.
Yes, sir.
You are making a point, but I need the explanation. If you want,
Please, I need help.
okay, more views.
Sir,
Juniors.
please. Stability.
Explain what you mean by
Sir, please.
stability.
An empty ship can be unstable and prone to capsizing, especially in rough seas. Tanks are used to stabilize the ship.
What is used to stabilize the ship?
Ballast tanks are used to stabilize ships.
Oh, okay. You are talking about something different. I'll explain. Okay, more views. I've seen more hands.
Sir, this can use to displace its own weight so that it doesn't sink.
Yes, you see, once in the aspect of its flotation, once the goods are out, it will become its mass will certainly drop, and so it will float easily. Okay, if there are goods, the goods would add to its weight, and yes, obviously the goods will also enable it to displace more volume of water. Now, if the moment the goods are taken out, the mass is less this time around. Okay, and so it will be lighter the more. But the reason why we have to fill it with sand is that it's due to stability, as said by those of you contributing. It's actually due to stability.
Yes, it's not stable.
For stability, what we mean is that, you see, if if the ship is just on the surface of the water, like somebody lying on an orthopedic bed, on the within the sea, or at some kilometers within the sea, the wind velocity is so much, and then the force is so much. So if you don't load it, there's the tendency that the wind would blow it and then topple it over. It can easily be capsized.
Yes.
Okay, that is why it must be loaded so that we have parts of it submerged under the water. So when it floats in such a way that we have some volume of it within, okay, it is difficult to topple the ship over than when it is just empty. So it is loaded due to stability. The strong wind, if it's stable, the strong wind cannot easily blow it and topple it over. Please, class, are we okay? So
Yes, please.
that is the reason. It's for Nanacho, your hand is still up.
Sir, please, a mistake, sir.
Okay. All right. Frank.
Please, can you also say that the density of the water will be too much for the boat to stay stable, therefore causing it to be capsized?
And that is it. You see, already we know that for it to float, the density of the object must be less than the density of the ship. And density of the object has to do with the mass and then the volume. So there is hollow cavity. So when you take out the load, the density of the body will be far, far less than. And that is how come everything, it will just be on the surface. Okay. So when loaded, it adds up to the mass. Okay. And it will make it more stable on the surface of the water. All right. Let's look at applications of flotation. Applications of flotation. Applications of flotation. The principle of flotation is applied in several gadgets or applications or in everyday activities. One, ships float. So it is applied in ships, canoes, submarines, submarines. Give me more examples.
Boat.
Yeah. Boat. Yes, Juniors, if your hand is up, please go ahead and contribute.
Sir, please, a raft.
Rafts, yes. Then let's also talk about the hot air balloon. Hot air balloon. Then I have Frank.
Life vests.
Come again.
Life vests.
Yes. Yes. Then we'll also talk about it is also applied in hydrometer. The principle of flotation is also applied in the hydrometer. We'll look at its application in hydrometer. We've talked about its application in ships, and we'll end up with its application in hot air balloon. These are the areas where the syllabus expect that we go into detail and then look at how it works. So I'm coming. Oh, somebody is giving me the information that I don't know if it's a he or she. Oh, okay, Michelle. She's not able to join. How come? Please, I'm coming. Let me forward the meeting ID to her in particular and see if that will sort the problem out. What is a hydrometer, class? Yes, what is a hydrometer? Hydrometer. Yes, anybody?
It is a meter used to measure.
Yes, I'm listening. Go ahead. It is a meter.
Used to measure water. Something.
You are learning. Go ahead. Yes.
That's all.
That's all.
Yes,
All right.
please.
Okay, thank you. Gideon.
So please, it is a meter that is used to measure the density of a liquid.
Okay.
So instead of saying meter, use it's an instrument.
Okay.
Okay. Okay, somebody is also saying that it's a tool used to measure the density or specific gravity of a liquid. Specific gravity is relative density. So it is used to determine the density of liquids. Okay. It's an instrument that is used to determine the density, and you can also say that the relative density of
Hydrometer.
yes of liquids. So when to determine the strength of acid in a car battery, you need a hydrometer to measure. Okay, you need the hydrometer to determine the strength of acid. All right. Now the hydrometer is just like it's like a pen with uniform cross-sectional area. I'm trying to sketch a hydrometer. With scale, graduated scales, markings here. We can also determine whether milk, the density of milk with this same instrument. 0, maybe 1, 2, 3, 4. I'm just creating my own graduated scale. Now, if this is Ella.
And sir, please have sent an image of a hydrometer on the page.
Okay. So Ella has just forwarded a hydrometer. Yes. That is a hydrometer. Ella, thank you so much. Now, when the hydrometer sinks more, it means the density of the liquid is less, or there's a drop in the density of the liquid. If it sinks less or floats more, then it means the liquid is denser. So if this is the hydrometer immersed or floating in a liquid, if this can go into it the more, then it means the density is less, that the density of the liquid is less, that the hydrometer can just move into it easily. If it sinks less or floats more, it means that the density of it, okay, I think I need to rather change the graduation. 0, 1, 2, 3, 4, 5. Rather, it must go up in this manner rather. So that if it sinks more, then it means the density of the thing is less, and it's okay in that order. So hydrometer is actually used to determine the density and relative density of liquids. Now, it also works on the principle of flotation, which is because the hydrometer must float in the liquid to measure its density, it obeys the fact that mass of the object, which is the hydrometer, must be equal to the mass of fluid displaced. Now, this mass of fluid displaced can be expressed as the density of the fluid, okay, product of the density of the fluid and the volume of fluid displaced. Please, are you there? Hello, class, are you there?
Yes, please.
Yeah,
Okay.
please, can you?
We are expressing the mass of fluid displaced in terms of the density of the fluid and then the volume of fluid displaced. So, mass of the hydrometer must be equal to the mass of fluid the hydrometer displaces. Now, this mass of fluid displaced by the hydrometer can also be expressed as the density of the fluid times the volume of fluid displaced. And don't forget, volume of fluid displaced, volume of fluid or liquid displaced can also be obtained from once we have volume of fluid displaced, don't forget we have the volume submerged. So volume of fluid displaced of liquid, let's use liquid because hydrometer is for liquid. Volume of liquid displaced is actually equal to volume of objects submerged. And we've discussed this before. Volume of objects submerged. Are we okay here?
Yes, please.
Okay. Now, the hydrometer at that part which must be immersed has a uniform cross-sectional area. So this area, the area of this part, which is A, must be uniform. If it has a uniform cross-sectional area, then we can also say that the volume of liquid displaced, which is equal to the volume submerged, H, can be equal to volume is area times length or height, right? So this can also be expressed as the uniform cross-sectional area A times the height of the hydrometer, okay, immersed within the fluid. And here I'm representing this by the letter H. And so volume of liquid displaced can be its cross-sectional area times the height or the depth of the hydrometer immersed within the liquid. And so mass of hydrometer is equal to density of the liquid times the volume of the liquid displaced, which is cross-sectional area times the height, where h equals the height of hydrometer submerged in a liquid. Class, are we okay? Hello, class, are we okay?
Yes, please.
Now, because the hydrometer has this cylindrical shape, we can also express its cross-sectional area A as the area is the area of a circle pi r squared, and so the volume of the hydrometer submerged, which is equal to volume of liquid displaced, can also be pi r squared times the height submerged within the water. So sometimes as teachers, we can set questions. Please, if you've just joined, mute yourself for me. As teachers, we can set questions which will look like determine the height of the hydrometer submerged. Okay, and this is what we expect that you use that to calculate for. Determine the cross-sectional area of the hydrometer, and you have to look for A. Determine the radius of the hydrometer, and this time around, A will translate into pi r squared, out of which you can be able to use that to determine the radius of the hydrometer. So it's all hinges on the principle of flotation, which is mass of the floating body, which is the hydrometer, is equal to the mass of liquid displaced by the hydrometer. Please, is there any question? Exactly.
Pi r squared.
Because you see, look at the what Ella dropped on the platform. Okay, the graduated part is cylindrical. So its cross-sectional area is actually the area of a circle. That is why, and the area of a circle is pi r squared. That is why it is expressed, the area is expressed as such. Frank, are you okay?
Yes, sir.
Ella, please look for the hot air balloon, a picture of the hot air balloon. Gideon.
So please, why are they using area of a circle in the formula?
Oh, that's what I just said. If you look at the picture, it has, you see, it's like this. This part is to ensure stability in the liquid. But this is actually the graduated part where there are scales to measure and all that. This area here depicts the area of a circle here. Okay. So the cross section, it has that uniform cross-sectional area. Then when it gets to the end, it curves. So my drawing is actually what's a drawing. So this is actually the part that is used. Okay. So when it is submerged in the liquid, this part enables it to be stable within. And this is where the height of the density is determined. So we are using pi r squared because of this part. It has a uniform cross-sectional area from Gideon this part to this part. Are you okay?
Yes, sir.
Let's look for the hydrometer. Sorry, the hot air balloon. The hot air balloon.
Sir, please, Frank has sent.
Okay. The hot air balloon. The hot air balloon is basically used for tourism purposes and for exploration. If you want to explore, look around, then yes, Frank, thanks for that's the hot air balloon. It also operates or works on the principle of floatation. Yes, Promasidor Ghana Limited introduced it into the country some years ago. Promasidor Ghana Limited, where celebrities like Mr. Abia, myself, were experiencing how the hot air balloon. Okay, so I happen to see a lot of celebrities going into it, taking pictures and all that. I don't know if you saw it. Cowbell introduced that into the country. Anybody here who saw that? Who saw the Promasidor Ghana Limited launching hot air balloon in the country some years ago? I think this was before COVID. Okay. So that's the picture of the hot air balloon on a platform. It is actually used for exploration. If you want to explore, look around. And it is also for tourism purposes. It works on the principle of flotation. Now, the sketch of the hot air balloon, there is a very vast balloon fabric. Very large balloon fabric. Then there is this basket. I'm just sketching something. Yes, this is the basket. The fabric, the balloon fabric, usually very, very large. It must be very large for a reason. The basket here is what harbors people who, the tourists, the explorers. So if you want to go into it and then look around, Anita, you will sit here. Emelda, Frank, you will also sit here. So these are the people on board. Now, if you look at the picture carefully, there is a fire chamber. There is fire within it. There is a fire chamber. Please, I hope you are looking at the picture. Are we there? Hello?
Yes, sir.
There is a fire chamber. Now, each and every part of it has its own purpose. The balloon must be large, extremely large, because the upthrust which enables the balloon to go up depends on density of the surrounding air times volume of air displaced times gravity. We have no control over the density of the surrounding air, natural. So we can't change the density of the air. But we can change the density, the volume of air displaced. How can we change the volume of air displaced? By varying the density of the object, because an object always displaces volume of fluid which is equal to its own volume. So if you want larger volume of air to be displaced, then the object must have a larger volume as well. So this is the reason why the balloon fabric is such that it must be of a larger volume in order to displace large volume of air to affect density. Then the balloon is also filled with light gas. These inert gases or these lighter gases such as hydrogen, helium, and argon. So it is filled with one of these inert gases. It can be hydrogen, it can be helium. Okay, now after it's been filled with one of the inert gases, the gas within must be heated to be warm. And this is the reason why there is fire chamber. Fire chamber. So the fire chamber is to warm the air, the gas which is within the balloon, so that the gas or the air within will be lighter the more. So if you are asked to explain why this and that, that's the reason. The fire chamber is there to warm the air so that it will be lighter the more. The whole idea is that we want to make the total weight of the balloon plus all the people on board to be less than the upthrust. So all that is done, the idea behind is that the choice of the larger balloon fabric, the filling of inert gas, the heating of the gas within, the idea behind it is to ensure that the entire weight of the balloon plus the people on board, entire weight of the balloon plus the people on board, the whole weight or total weight is less than the upthrust produced by the surrounding air. And if upthrust is greater than the surrounding air, then the balloon can easily move up because we have the total weight acting in this direction. We have the upthrust produced by surrounding air in the opposite direction. So if U is greater than W, when two forces act and one is greater than the other, the net force takes place in the direction of the larger force. So if U is greater than W, the net force would be in the direction of the upthrust. So the balloon can easily move up. This is how the balloon is launched. Secondly, when the balloon is being launched, it must be launched at windy areas, just as this paragliders. During paragliding, it is not done at any other place. It must be done at an altitude where the area is windy. Class, are you there?
Yes,
Class?
please.
So this is how the balloon will take off. The balloon will take off if its total weight, the weight of the balloon, the weight of the gas within, the weight of the people on board is less than the upthrust provided or supplied by the surrounding air, then the balloon can take off comfortably and go up. Is there any question here? If you have any question, ask before I continue. We have about how many minutes to go? Seven. Please, is there any question? Okay. My question, if you have no question, my question to the house is that we are just saying that if the upthrust is greater than the entire weight of the balloon plus the people on board, the balloon moves in the direction of the upthrust. So it will go up because upthrust is an upward force. Hold on.
I'm coming.
So the question is that if the upthrust is greater than the total weight, the entire weight of the balloon, then we expect the balloon to go up so it enters heaven, right? Class, I hope you are following.
Yes.
So if the upthrust is greater than the total weight, then the balloon must go up and get to heaven. But that does not happen. That does not happen. It goes up for a while and then this time around it's stable to float in the air. Why? Yes. I think one hand is up.
Sir, please, they use sandbags. So if they drop one sandbag, the lighter it becomes and the higher it goes. But as they keep it, it helps maintain the same weight so that they don't go beyond reach.
Sorry, Frank. I will not well express, but I will not buy it. More views. If you have raised up your hand, please go ahead.
Sir, please, in the beginning, you said for the hot air balloon to be able to take off from the ground, the weight of all the people there must and the air which is
the
inside
balloon
must be less than the density of the surrounding air. So as it goes higher, the density of the surrounding air changes and it also increases. So it will get to a point, it will stop because as it goes higher, it decreases. So the weight of the people and the air in the balloon is
Frank, as it goes higher, what decreases?
The density of the surrounding air.
Okay. Can you tell us why?
Because as you go higher, the gravity acting on you will be less.
And so, Frank, I'm listening. Gideon. Okay, I think. Oh, Juniors, you want to say something?
No, that's
Sir,
that's all.
please. So, sir, please, as it goes higher due to the force of gravity, it makes the air around it dense. So, meaning that the force bringing it down becomes same as the upthrust, causing it to float.
Okay. Okay. I think nice contribution so far. Nice contribution so far. Let me then come in. So the idea is that as you see, naturally, the higher we go, the lesser the density of the air, the surrounding air. Look at oxygen, for instance. As we go up, the concentration of oxygen decreases, meaning the density decreases. So when you go up, the mountaineers, those who climb mountain, if they are going up, they need to go with their own store of oxygen. Else, it will come to a point where breathing becomes difficult. Okay, confirming the fact that the higher we go, the lesser the concentration or density of air. So as we go up, density of air decreases. Okay, so at a particular altitude, because the upthrust, which must be greater than the entire weight, depends on density of the air, volume of air displaced, and gravity. V and G, yes, G decreases as we go up. G decreases as we go up. V is constant. And here is the case, rho is also decreasing. So if these are decreasing, then clearly U would also be decreasing as we go up. At a particular altitude, we'll have a situation where the upthrust is just equal to the entire weight of the balloon plus all the occupants. And this is the point where the balloon floats, because you see, this equation satisfies the condition for flotation. For a body to float, the weight of the body must be equal to the upthrust. So when U is equal to W, then the hot air balloon will not go up again, but it will be floating within the air. So this is how come it will not go up, enter into the sun or go to heaven, but at a particular altitude, the balloon would float in the air. Please, is there any question? Okay. All right. So if there is no question, it's exactly 12 o'clock. Please, if you have questions, you can forward it to me as well. Or contributions. I'll also take notes and then discuss it with the house in our next meeting. Okay. So please, I'll forward your assignment as usual. Those of you who are fond of not submitting assignment, I beg you, do the needful, because I'll be giving records on a page. Until next week, may the good Lord be with you. Take care of yourselves and bye-bye. Okay.
Bye.
This time I'll upload a video. All right. Yo. Bye-bye.